Today we're going to talk about force. Not the force with Darth Vader and Luke Skywalker, but the force that we talk about in physics. So what is force? Well, force is probably best described as a push or pull on an object. Push or pull on an object. All right. So Newton's second law tells us that an unbalanced force will cause an object to accelerate. Well, I guess it means we have to understand what the word accelerate means. And we have to do a little background in order to get to that answer. So let's start with what we do know, speed. We know that speed is equal to distance over time. We're all familiar with things like 55 miles per hour. Miles per hour. All right. So velocity is related to speed. So velocity is simply speed but with a direction added to it. So instead of just being 55 miles per hour, it would be 55 miles per hour east. So velocity is speed and direction. Acceleration is defined as a change in velocity. So a change in either the speed or the direction. And that's important to remember that it could be either or both. So a change in the speed or the direction. Let's look at some examples. So here we have an unbalanced force. And an unbalanced force we know is going to cause an object to accelerate. It's going to accelerate in this direction. You have 200 newtons of force. There are no other forces acting on this block that would cause it to be a balanced force. So unbalanced forces accelerate. Well, how about balanced forces then? Here you can see with this block, we have a balanced force. We have 200 newtons of force pushing to the right, and we have 200 newtons of force pushing to the left. So this is balanced. Well, if we said that an unbalanced force accelerates, then the opposite is also true. A balanced force does not accelerate. So if it's not accelerating, what does that mean? Not accelerating? Not accelerating means that there is no change in speed. It's a constant speed. Do we know what that constant speed is? Nope. That constant speed could be 200 miles per hour, 4 meters per second. That constant speed could even be zero. 0 meters per second is a constant speed. And there's no change in direction. Okay? So when we have balanced forces, the only thing that we can say about this block is that it's not changing its speed and it's not changing its direction. I can't say if it's moving, if it's not moving, what direction it might be moving. None of that information is given to me here. All that I can say is that because there's balanced forces, I know that it is not accelerating. Unbalanced forces accelerate, balanced forces do not accelerate. They have no change in speed and no change in direction. So let's take a look at Tenderheart Bear here. Is Tenderheart Bear accelerating? Well, look at the forces applied to him. We have 10 newtons going to the right. Is he accelerating? He sure is. What would happen if I took this force, instead of making it a push, I made it a pull? Would he be accelerating now? Absolutely. A force is a push or a pull. It doesn't matter either side. And he is going 10 newtons of force to the right. There's no other balancing force. So is he accelerating? Yes, he's accelerating to the right. Now it's important that we know when we talk about accelerating, we don't think about it in the same way that we do in our car. Acceleration can be both positive and negative. We don't even know what direction he's going. Tenderheart Bear could be, in fact, moving this direction quite quickly. But that force right there would just be slowing him down, slowing him down, slowing him down. He would be decelerating or negative acceleration. So I can't tell anything about which direction he's moving. All I can say is that the Tenderheart bear is accelerating to the right. All right, how about this situation? We have 100 newtons to the right, 40 newtons to the left. I'm going to ask a new question now. I'm going to ask, what is the net force on this awkward dinosaur? Well, if it's going 100 newtons this way and 40 newtons in the opposite direction, well, then we just do basic math. 100 minus 40 gives us 60. The difference is 60 newtons. And what direction is it going? Well, it's going to the right. So the net force is 60 newtons to the right. Are the forces balanced? No. We know that those forces are not balanced. 140 are not equal. Is the awkward dinosaur accelerating? Since they're not balanced, we will say yes, they are accelerating. Now what if we change the situation a little bit and we added in another force? So we added two forces together. Not only do we have this 40, but we also added a 60 Newton force here. So two forces acting on the awkward dinosaur to the left, one to the right. And these add up 60 and 40 to 100. And here we have 100. Then we would say that the forces would be balanced. All right. How about this situation? What is the net force on the soccer ball? 100 newtons to the left, 100 newtons to the right. Well, it's a balanced force, so there is no net force. Are the forces balanced? Yes. Is the ball accelerating? It is not accelerating. We know that balanced forces do not accelerate. Unbalanced forces are accelerating. That's Newton's second law. So is the ball accelerating? No. Is the ball moving? I don't know. Maybe. I know that it's not speeding up and it's not slowing down. It's not changing directions. That's all that I know. All right. How about this situation? It's a little more complex. We have 25 newtons going down, 50 newtons going up, 100 newtons going to the right, 100 newtons going to the left. Well, these 100 newtons balance out. So these are balanced forces. We don't have to worry about these. So is he accelerating to the left or to the right? No. Now let's look at the up and down direction. We deal with the different directions differently. Going down, and he's got 25. Going up, he has 50. So what is the net force on the Sleeping Cthulhu? Going up, it is 25 newtons. Are the forces balanced? 50 versus 25? No. Is the Sleeping Cthulhu accelerating? Yes, he's accelerating, going up. So is he accelerating? Yes. All right, so let's talk about the units of force just a little bit. We've talked about them in every one of these examples, but maybe we haven't explained it. The unit of force is a Newton. And Newton, obviously, is named after Sir Isaac Newton, who put together our three basic laws of motion. They used the term Newton because it was easier than the units that force really was. So you need to know that a Newton is the same thing as a kilogram meter per second squared. Now that does not make a whole lot of sense to me. I'll be honest. I can't envision what a kilogram meter per second squared is. But that's what a Newton is. Now where do they get that from? Well, it comes from the formula for force. And we've mentioned this before. The formula for force is force equals mass times acceleration. So formula for force is mass, kilograms, times acceleration. You have to trust me on this one. Acceleration is meters per second squared. How fast is the speed increasing? Kilograms times meters, all that over second squared. Now that you know the formula for force, you can start doing some problems dealing with force, mass, and acceleration using the guess method.